In this exercise, there's also a new term introduced, and it's called the normal. The normal. Now, the normal is a straight line. It, by definition, is perpendicular, and you can see I've drawn the little perpendicular symbol here, and it's perpendicular to the tangent. So that's pretty convenient. If it's perpendicular, you know that its gradient multiplied by the gradient of the tangent. So I'll say tangent normal here. Multiply the gradient of the tangent, the gradient of the normal, you'll get -1. Or the gradient of the normal is -1 on the gradient of the tangent. And the other feature of the normal is it passes through the point of contact between the tangent and the function. Now, knowing that, you can see that these common applications will actually make some sense. It says, questions commonly require the equation of the actual tangent, which is the equation of a straight line. What do you know about the equation of a straight line? There are many different ways of getting the equation of a straight line. And the normal. What do you know about a normal? It's a straight line. What do you know about getting the equation of a straight line? There are many different ways. At a particular point on a curve. So we're getting the equation of these two straight lines at a particular point. So both a straight line and a normal, a tangent and a normal are straight lines. It'll be necessary to use the method for getting an equation of a straight line learnt in Chapter 5. Since this is about derivative is about gradient, you know that one of the methods is going to probably have something to do with using the gradient, finding the gradient and using the gradient. And the connection between the tangent and the normal is their gradient. So I'm pretty confident that gradient is going to be used in the method. And because it passes through a point, both these lines, the tangent and the normal, pass through a point, it probably stands to reason that we would use y minus y1 is m times x minus x1 to get the equation of either one, because x1, y1 is a point and m is a gradient. Okay. But it looks now in these examples, we're just practicing our differentiation. Practicing setting out, using appropriate notation. There'll be some rearranging if necessary. And let's see how we go. So if you're asked to differentiate 5x minus 9, what do you notice about this? This expression 5x minus 9 is not given any name. It is not written as y equals 5x minus 9. But if it was, our notation for the derivative would be, one option is dy dx. Or we might choose to use a very brief notation, which is a y dash. And if it had been named f of x is equal to 5x minus 9, we would use the notation for the derivative as f dash x. Now, it hasn't been given any name, and we don't need to give it a name. What we can say is we're just going to differentiate this, so just a d on the top, not differentiating y, the y expression, with respect to x, but just differentiating with respect to x this expression, and the answer would be 5. Likewise, with this next one, 2x to the half minus 3x to the minus 1. Things I know now, we've got two little, I suppose, two little functions together, forming a function, we will differentiate each part of this by bringing the power to the front. There's no complication. There's a power. We can bring it to the front and multiply and subtract 1 from the power. And again, no name given to this. So the notation I'm going to use is I'm going to differentiate with respect to x, and I write the expression I'm going to differentiate, which is 2x to the half minus 3x to the minus 1. How do I do that? Bring the power to the front. And again, once I start differentiating, I don't write d dx. Once I've differentiated, I go straight to what the expression is, which is a half times 2 times x to a half minus 1. Minus, bring the power to the front, times, another negative 1, bringing the power to the front, times 3 times x to the minus 1 subtract 1. Half times 2 is 1, and this is x to the minus a half. A negative and a negative make a positive. 3x to the minus 2. Be careful with your subtraction in this case. Directed numbers. I'll go down under here. X to the minus a half may be written as 1 over x to the half plus 3 times 1 over x squared, and this may be written, x to the half may be written as square root of x, and this goes together, 3 over x squared. Now I've tried to speed this up a bit, and as you can see I've written the solutions there, but I'm going to go through and talk about them now. So this wasn't named again as in any ways, so we would just say d dx of that expression. It's the addition and subtraction of some little terms which are all nicely in the format such that we can bring the power to the front and subtract 1 from the power. No complication in this really, just using the shortcut. 3 2s are 6x squared, 7 2s are 14x plus 7. Not sure why I put the exact same question in again. It's saying d dx of this expression. Everything's good, x all 2 got a power, and we can differentiate, but it's the exact same expression. So it's 6x squared again, minus 14x plus 7. With this one here, now this is unusual. I guess it will happen, but it's not very good practice on the part of the person setting the question. They've named the function y. So normally, yes, we would talk about dy dx. However, they go on in the question to say find f dash negative 2. We can understand what they mean. Find the value of the gradient when x is minus 2. And I guess that's the drawback when you use dy dx and you want to then talk about the gradient. Whereas if you're using f of x, you can talk about the gradient just in abbreviated notation form by using f dash. Okay, so what I've done, and the expression's all nice, x to the 4th minus 2x cubed plus 5. It's all nicely set up such that we can bring the power to the front and subtract 1 from the power. So I've actually used the notation that they have in terms of they called it y. I'm going to call it dy dx. And I'll get 4x cubed minus 6x squared. But what do we know? We know dy dx is exactly the same thing as f dash x. These are exactly the same. They give expressions for the gradient of the tangent. So f dash of x then must also be this 4x cubed minus 6x squared, which allows me then to say f dash negative 2. Put a negative 2 in the spots for x, negative 2 in those spots. Just be careful, cubic of a negative is negative. We've got another negative here, and we get minus 56. Now, for the first time, we have a bit of a problem. Why? Because have a look at what we're finding. Not only do they not name it, but also we can't see the power that x is being raised to. So we're going to rewrite it. d dx of the fifth root of x is d dx of x to the 1/5. Again, this is why we revised indices. Now once I've written it in this format, it's very easy to differentiate. 1/5 x to the 1/5 minus 1, and so on. When we get here to the answer, there's actually two ways that it can be written. And you might choose to give both. I'll stop the video there and do the rest in another video.